One situation that often comes up in optimization examples is sometimes once you have your function written down that you want to find the minimum or maximum for, you'll find that the domain that makes sense is not a closed and bounded domain. And that's a little bit problematic because the extreme value theorem, which we've been using to guarantee that there is an absolute minimum and maximum, only applies to closed and bounded intervals. So if the interval that is your domain isn't closed and bounded, you have to be extra careful because the extreme value theorem doesn't help or doesn't guarantee that the absolute minimum or maximum exists. Now, if you're trying to solve an optimization problem, then hopefully the absolute minimum or maximum does exist, but we won't be able to use that shortcut of just checking critical points and endpoints. Right? We'll have to think a little bit harder about what is going on with the situation to guarantee that any local minimums or maximums that we find are actually absolute minimums or maximums for the domain that we're thinking about. So here's one example where that kind of thing happens. So suppose we need to design a cylindrical can to package 500 cubic centimeters of some new product, some new coffee drink. If the sides and the bottom of the can cost 1 cent per square centimeter and the top of the can costs 2 cents per square centimeter, maybe the top of the can has to be a little stronger, so it's a little more expensive to produce. What are the dimensions of the cheapest can? Right? We don't want to spend any more on the packaging than we have to. We want to deliver our delicious coffee drink instead. Since we want to find the cheapest can, that's really the minimum cost, right? So what we need to do is express the cost of the can as a function of something. Well, its size is what it's going to be a function of, right? Because its cost is determined by how much surface area there is on the sides and bottom, and then also on the top. So we'll write the cost as a function of the dimensions of the can, and then we'll minimize that cost. But there is another constraint to this situation. We only have to consider cans that have 500 cubic centimeters of volume. So we need our volume to be 500 cubic centimeters. All right. Well, we're making a cylindrical can, so right, if we have a cylinder like this, then the important measurements are the radius of the base and also the height. So the volume of this can is, let's see, it's the area of the base, which is pi r squared, times the height. Okay. So here's a relationship between the two measurements, the radius and the height. So what we can do is use this to somehow eliminate one of these variables, either the radius or the height, once we've expressed the cost as a function of these dimensions. All right, so what is the cost of this can? So it's the cost per unit area of the top. So it's cost of the top plus the cost of the sides and bottom. Okay, so the cost of the top is going to be 2 cents per square centimeter. Times the number of square centimeters, which is going to be the surface area of the top. So what is the surface area of the top of this can? Well, the top is just a disk, so that's pi r squared. Okay, plus, now for the cost of the sides and the bottom. Well, the sides and the bottom are 1 cent per square centimeter. Okay, times the surface area of the sides and the bottom. So the bottom is just a disk, so the bottom is pi r squared again. What about the sides? Well, let's see. The circumference around this thing is 2 pi r, and then times the height to get the area of the sides. So we need to add the circumference, 2 pi r, times the height. Okay. Now that we have this all written down, right, this is going to be in square centimeters. This stuff in parentheses, this is also going to be in square centimeters. So you can see the square centimeters cancel, and we are getting something in cents, which makes sense because the cost is going to be some amount of currency, which is a number of cents in this situation. All right, so now that we see that the units work out correctly, we don't have to keep track of the units as we do the rest of this calculation. So let's clean things up a bit. So this is 2 pi r squared plus, let's see, 1 cent. Let's see, pi r squared plus 2 pi r h. Okay, we can combine these. So this is 3 pi r squared plus 2 pi r h. Okay, now you can see this cost has come out to depend on the radius and the height, but to use our optimization procedures, we need to express this as a function of just a single variable. But we can use this volume relationship to eliminate one of the two variables, and we get to choose which variable we eliminate. We choose which variable to eliminate by solving this equation, this volume equation, for the variable we want to eliminate. Well, solving this volume equation for r would involve taking a square root, and that's going to make a mess. I don't like having square roots around if I can avoid it, especially when I'm doing calculus, because it just kind of makes a mess once you take a derivative. But if we solve for h, we won't have to take any square roots. So let's solve this volume equation for h. We get h equals 500 over pi r squared. So we can take this and put it into our cost formula so that we're expressing cost only as a function of r. So cost as a function of r is 3 pi r squared plus, let's see, 2 pi r times h, but h is 500 over pi r squared. So let's simplify this. 3 pi r squared plus, let's see, 2 times 500 is 1,000. The pi's cancel and one of the r's cancel, so 1,000 over r. All right, so here's our cost function, and this is what we want to minimize. We need to come up with a domain that makes sense. So what is the smallest domain that makes sense? Well, the radius definitely can't be any smaller than 0, but in fact the radius can't actually be 0, because then we couldn't make the volume be 500, right? If the radius is 0, the volume is going to be 0. So to make the volume 500, the radius has to be strictly positive. So r has to be strictly greater than 0. You can see in the formula that r can't be 0 because you can't divide by 0. But there's also sort of a geometric reason that r can't be 0. What is the largest possible value for r? Well, let's see. I mean, if you just imagine making this radius bigger and bigger, the larger the radius, the smaller the height, because remember, we need a volume of 500, but there actually isn't any limit to the radius, right? You could make the radius of this can as large as you want, as long as you made the height as small as necessary to make the volume be 500. So actually there is no upper bound to what the radius could be. So, you know, we were hoping maybe to have something out here, but no. The radius could be anything that's positive. So in this situation, our domain is not closed, because it doesn't include its endpoint, right? This isn't less than or equal to. Also, it's not finite, because going in the positive direction, this domain stretches out to infinity. So when we go to find the minimum and maximum values for, I guess, just the minimum value for this cost function, we're going to have to think carefully about, you know, if we find a local minimum, we're going to have to think carefully to really convince ourselves that the local minimum is an absolute minimum. All right, so with that in mind, if there is an absolute minimum sort of in the middle, not out towards infinity, then the minimum will be a local minimum as well. So let's see if we can find any local minimums. To find local minimums, right, this function is differentiable everywhere it's defined, so we don't have to worry about undefined derivatives. So let's just take a derivative and then set it equal to 0. So we get 6 pi r minus 1,000 over r squared. Yes, now we need to set that equal to 0. Okay, solve this equation, so let's multiply both sides by r squared. We would have to worry about, right, we would have to worry that we could be multiplying by 0 if r could be 0, but remember, we've specifically excluded the possibility that r is 0. So, let's see, multiply everything by r squared, we get 6 pi r cubed minus 1,000 equals 0. So isolate our r cubed. R cubed is 1,000 over 6 pi. So maybe we should write that as 500 over 3 pi. And then take cubed roots. So r is the cubed root of 500 over 3 pi. So that is a pretty awful looking number. Just to have some idea of what that actually comes out to be, let's calculate that. So third root of 500 divided by 3 times pi. I think that this calculator didn't do that right, so let me try that again. Let's see, 500 divided by 3 times pi. When in doubt, use more parentheses. To the power 1/3. I'll enter it that way. Okay, yeah. 3.757.5. And this must be in centimeters, I guess, since we're measuring centimeters in this problem. Okay, so we have a critical value here. We don't know that it's a minimum. That's one thing. And the second thing is, even if it's a local minimum, we don't know if it's an absolute minimum. We're looking for the absolute minimum cost. So, right, we don't have any guarantee that, a priori, right now, we don't have any guarantee that even if this is a local minimum, it's an absolute minimum. So we're going to have to think a little harder. Well, one thing we can do is check if it's an absolute minimum, or sorry, check if it's a local minimum by using the first or second derivative tests. Let's use the first derivative test just because, I don't know, just because it always gives us a result. So to use the first derivative test, remember what we're going to do is make a sign chart for the first derivative. So we know that the domain we're interested is greater than 0, and we need to put our critical value on here, which is 3.7575. I'm going to stick to the decimal, I think, rather than write out this cubed root every time. And there is no right-hand end to our domain, right? It goes all the way out to infinity. So there are two intervals that we need to check, from 0 up to our critical point, and from our critical point out to infinity. So let's see, we could plug in 1. If we evaluate c prime at 1, we're going to get, let's see, 6 pi minus 1,000, which definitely is less than 0. So our derivative is negative in here. And what about, let's see, we could plug in, I don't know, how about 100? Right, that's going to be out here somewhere. Oops, 100. So that's going to be 600 pi minus 1,000 over 100 squared is 10,000. So that's going to be 1 over 10. That's definitely positive. So over here, the derivative is positive. And at our critical point, the derivative is 0. So this tells us two things. So the first derivative tells us that this critical value is a local minimum, because the derivative at this critical value, the derivative is going from negative to positive. So it has to be a local minimum. But also, it tells us more than that, because if we use this sign chart to make an extremely rough graph an extremely rough sketch of the graph of C, right, the graph is going to be decreasing here. It's going to have a horizontal tangent line at our critical value, and then after that it's going to be increasing. Well, even with this just extremely rough sketch of the graph of our cost function, you can see that this local minimum, it has to be an absolute minimum, right? In principle, it's possible that, right, if you have a local minimum on some graph, it's possible that the graph could have lower values further to the right, even though there's no critical point over here, right? This part of the graph over here has no horizontal tangent lines. But, for this to happen, you have to have some decreasing portion of the graph at some point, but we don't have any decreasing portion of the graph to the right of our critical value. So our critical value not only is a local minimum, it's actually an absolute minimum. So now we're sure that it's an absolute minimum. All right, and that's what we wanted to find, right? We wanted to find, I think, the dimension of the can that gave us absolute minimum. Yes, dimensions of the cheapest can. So we know that the radius, so dimensions of the cheapest can are, let's see, the radius was this critical value that we worked out, 3.7575, and the height of our cheapest can, well, we're going to need to use our height formula, which is way up here somewhere. There it is, 500 over pi r squared. So 500 over pi times 3.7575 squared. And might as well punch that into a calculator, I guess. 500 divided by pi times 3.7575 squared, closed denominator, equals, okay, 11.272. Okay, and these are both in centimeters. So there's the dimensions of the can that gives us our lowest cost. All right, let's look at another typical situation that involves a non-closed or non-bounded domain for an optimization problem. This one's just a geometry problem. Let's find the point on this parabola, y equals 1/2 x squared, that's closest to the point 4, minus 1. So 1/2 x squared, that's going to look something like this. And 4, minus 1, that's out here somewhere, right? Definitely it's not on the parabola, because if you plug this point into this equation, it does not work. It does not make the equation true. And in fact, it's below the parabola. So let's find what the closest point on this parabola is. What we're going to have to do is, so I guess first thing we need to do is figure out what is it that we can control. Well, what we can control is which point on the parabola we're choosing, right? So this point over here, 4, 1, that's fixed. But we can choose any point on this parabola. And points on this parabola always look like x, 1/2 x squared. That's what makes them be on the parabola. So what we can do now is write down the distance from the point on the parabola to our fixed point. So I'll use a capital D because lowercase d is special in calculus class. So d, distance as a function of x, is, we're going to have to use the distance formula. So square root, the difference in x coordinates is x minus 4 squared plus, and then difference in y coordinates is 1/2 x squared minus 1 squared. All right, and the domain for this function, well, any x value is going to give us a point on this parabola, so this domain, the domain that we need for this is all real numbers. So, right, extremely unbounded domain. Well, this would work. We could solve the problem this way, but there's actually a nice trick. This is something to keep in mind. When you're solving an optimization problem, you don't have to always find the minimum or maximum for the value you want. You could find the minimum or maximum of some closely related value. So rather than finding the minimum distance, right, which is what we would need to do to find the closest point, we'd need to find the minimum distance. Well, instead we could find the minimum square distance. Right? And that would be nicer because then we wouldn't have to have this square root. So instead of minimizing this function, what we can minimize is the square distance. So the square distance function is just x minus 4 squared plus 1/2 x squared minus 1 squared. You can see this equation is going to be easier to solve. So, this function is going to be easier to find the minimum of because the formula for it is just simpler. All right, so let's see. We're going to have to take a derivative, and maybe we should multiply this out before we do that. Couldn't hurt, I guess. So when we multiply this out, we're going to get x squared minus 8x plus 16 plus, and then multiplying this mess out, we get 1/4 x to the 4th minus x squared plus 1. Yeah. Look, the x squareds cancel. That's kind of nice. So 1/4 x to the 4th minus 8x plus 17 altogether. All right, and that's our square distance function. I'll call it SD for square distance. Okay, now we need to find critical points. Incidentally, in this example, you can tell that there isn't going to be an absolute minimum, or there isn't going to be a minimum out that way because distance gets big out there. And there isn't going to be an absolute minimum distance out that way because the distances get big over there as well. So really, it seems quite plausible that the minimum distance is going to be in here somewhere. In fact, it's a certainty, right? So let's find critical values by taking a derivative. So derivative of our square distance function is x cubed minus 8. So let's set that equal to 0. This derivative does exist for every x value, so no critical values coming from non-existent derivatives. Set this derivative equal to 0, and we actually get a really nice value, x equals 2. Okay? So this is the only critical value that we get. So let's make a sign chart for the first derivative to see if this critical value is a local min or a local max, and maybe the sign chart will guarantee that we have an absolute minimum here. Right? Remember, geometrically, we are going to have an absolute minimum here, but it's good to know that that comes from the sign chart. Okay, so we need to choose some x values for test points because we have 2 intervals that we need to figure out here for our sign chart. So how about we use, 0 and 3. Those seem good. So let's evaluate this derivative at 0. We get minus 8. That's negative. So the first derivative is negative here. And how about we plug in 3? So 3 squared is 27 minus 8. That's positive. So positive here. All right. All right, so now we can see that, again, the square distance function decreases up to our critical point where it has a local minimum by the first derivative test, and then it increases from there, and so x equals 2 is an absolute minimum. All right, and so we can use this point that produces the minimum distance to find the closest point. So remember, the points on the parabola look like x comma 1/2 x squared. So now we can plug in our x value to find the closest point. So it's going to be 2 comma, let's see, 1/2 2 squared, so that's 2. So the closest point to 4 comma 1 is 2 comma 2.